So uniform circular motion examples are pretty straightforward. There's nothing too complex about it. Let's just say that, for example, let's take my ball on a string. For my ball on a string, I've got in the video that I did, maybe the radius, the string length was about 0.5 meters, and I was rotating it. I chose to rotate at a speed of approximately, I believe it was actually, I think I actually timed it. The period was about 0.7 seconds. The period of rotation. And let's go ahead and ask, what is the various variables that we haven't defined yet? What is C, F, speed, circumference, frequency, speed, and centripetal acceleration, magnitude of centripetal acceleration? Well, it could be the vector. We can't really answer the question, the velocity at any instance. Let's ask that. Circumference, frequency, velocity, and centripetal acceleration. So we can start with circumference. Circumference is 2 pi r, which is 3.14 meters. Frequency, which is 1 over period, which is 1 divided by 0.7, 1.43 hertz. Velocity, which is, or speed, let's start with, which is 2 pi r over t, or 2 pi r f, which is 3.14 divided by 0.7, 4.49 meters per second. Is it meters per? Yeah, because those are the units I gave. So what's the velocity? Is that in the tangential direction, right? It's not in the x or y or anything. It's tangential. Okay. Acceleration, centripetal acceleration, is speed squared over r. It's not velocity squared. It's speed squared over r, which is 4.49 times 4.49 divided by r, not t, divided by r, which is divided by 0.5, which is 40.3 meters per second squared, and the direction is inward. Okay, so those are pretty much all the variables we could define. That's just my ball on a string. Oh, I didn't even draw the picture, right? Ball on a string going in a circle. Terrible drawing, but okay. So one of the things I want you to notice here, this is interesting, it really is interesting, is look at the value of the acceleration. This is a ball on a string. It's not a particularly strange situation. I sat in the lab and I put a ball on a string and I rotated it pretty much at this distance and period. But look at that acceleration, 40 meters per second squared. What you should recognize is that's a pretty big acceleration. That's approximately equal to 4g. That's 4 times the acceleration due to gravity. Now, we talked earlier on about what's a large acceleration, what's a small acceleration, and 4g is getting for a pretty big acceleration for a person, right? That 5g is a sort of limit of what you really want to take. Above that, you sort of got to train for it. Air Force pilots at most 10 Gs. So the point that we see when we start talking about uniform circular motion is that accelerations are actually, where we get high accelerations are not necessarily from changes in changes in speed, but it's changes in direction. It's when you're going around a circle. That's when you get the higher accelerations. Or that's when it's easier, or when you tend to get the higher accelerations. You can certainly get acceleration from changes in speed too. But think about the stereotypical roller coaster ride. Where do people feel the weirdest, right? Feel like they're getting the most force, or they're the dizziest? It's when you go around a circle. So let's say, for example, another example is how fast would a roller coaster have to be going in order to get 10 Gs? I don't know. I'm making this up. 10 Gs is a very unreasonable acceleration for a roller coaster. So let's just say that we've got a roller coaster. Let's just pretend we've got maybe that's not a roller coaster. Maybe it's a ride where we're training an Air Force pilot. But let's just say we've got an acceleration, a magnitude of acceleration of 10 Gs. Let's say we put them in this ride, and so they're sitting in a sort of a merry-go-round kind of thing. And you've seen this actually on movies and TV before, where they actually test the pilots or the astronauts in this thing where they rotate them. And think about what the radius of that thing is. The radius, you know what I mean. There's a room, and they put them in sort of a seat that's attached to an arm, and the thing just goes around, and it makes them pass out, right? And I'm thinking it's sort of room sized. Maybe the radius is 5 meters. I don't know. Maybe the radius. 5 meters. 5 meters. So let's just say that we've got somebody in this apparatus where we're testing Air Force pilots, and we want to see if they can withstand 10 Gs. So put them in this thing that has a radius of 5 meters. And ask at what speed is needed for that 10G acceleration in order to make them pass out, right? So now it's a pretty straightforward plug-in. AC equals V squared over R. So 10 Gs is equal to V squared over 5 meters. And so it's 10 times 9.8 meters per second squared times 5 meters equals V squared. And so therefore, the speed required is 22 meters per second. So you can see that's actually not a very high speed, right? It's about 45 miles an hour-ish, somewhere in there. It's not very high speed. Roller coasters go far faster than that, which tells you that roller coasters, you got to be really careful about the curve length, right? The curve radius of a roller coaster. You want to, if you're going 50 miles an hour on a roller coaster, you can't go around a corner with a radius of 5 meters. The acceleration is way too high. You've got to slow that roller coaster down if your corners are that tight, or you've got to make the corners less tight. We'll talk more about roller coaster loops when we get to the fourth chapter.